All right, we're back. Ready for more fun? We had a request to re-explain our answer for part 5. So what I've done is I've pared it down to the amount of information you will get on Wednesday. We always start by getting rid of spectators. There's 2 of them there, which means we had 2 minuses here. We had 1 minus here. We always start with the pair that's already there to determine which one's the acid and which one's the base. In the fully protonated version of arsenic acid, there would be 3 protons. In the diprotonated version, there will be 2 protons. In the monoprotonated version, there will be only 1. Which of these 3 forms do we have as the acid in this pair? 1, why is this the acid in this pair? It has more protons, 1 more proton than its conjugate base. How many protons does it have? 2. So it's the second number. pKa is 6.9. Every time you write down a pKa, do the pKb for its conjugate base immediately. I don't even know if I did. I can't remember doing this on the other one. I might have forgotten this part. So that's 7.1. Acids react with bases. This will be the conjugate base of that. We have to figure out which acid will be lost going from the left to the right. Acid becomes base. We must take the lowest pKa that remains off of this molecule. This hint tells us one thing. We've got, well, look for all the changes. We got in this fully deprotonated form. This is the deprotonated version of this. This is the protonated version of this deprotonated version. And the SH is protonated here. And that's an S minus down here, deprotonated. And the one that didn't change because it was missing in this one, triprotonated means, what does it mean when it says triprotonated and you were given 4 pKa's? It means 1 proton is missing, not 2, not 0, 1. 1 proton missing. You still have 3 out of the 4. So if I know what it looks like when all of the protons are missing, that's what fully deprotonated means. And I know what it looks like when only one of them is missing, then I know these 3 got taken off for this to become fully deprotonated. Which of these 3 is going to come off first? Well, the first one that came off, why is it off? Well, it was the first pKa. It's the easiest one to take off. It's the conjugate base of a carboxylic acid. Does it make sense this number is pretty close to 5? Yeah, because carboxylic acids are 5. There's other effects going on here too. But that number 3.9, we're not going to be using it. No. The question is, of these 3, which one am I going to take off and draw the product right here? And we have to use what's given here. And if you didn't learn what I said about THI, you're going to be doing yourself damage. It's such a common thing in biochemistry, the THI prefix, but learn it now, that means sulfur. So you know the 8 is here. And the sp3 ammonium, you don't have to do this on this question. I know my answer. 8 is the answer. It's the lowest of these numbers. There's the sp3 ammonium. And here is the must be the other one. Don't even need to know what it is. It's the only thing that changed here that hasn't been accounted for. And which of those three, an 8, a 10.5, or a 12.5 will react first? And the answer is the 8. Lower pKa means stronger acid. pKb is 14 minus 8. I think I forgot to do that on the other one too. Okay. All right. Now we have to draw the product. Now I had trouble. I couldn't figure out a way to circle everything in the molecule except for SH. So here's what I did. I'm going to go slow. I just redrew the CH2SH right down here. And then scribble this out. And that arrow is now pointing at this. That didn't change anything. I just drew it so I could do a circle better. Light pink, everything up to the CH2. Make sure you circle everything in the molecule that's included. Please, if you don't call it R and you just have an R show up here, you're going to lose a whole point. You got to tell me what you mean. When SH loses a proton, it becomes S minus. And the pKb of that is 6. Then you finish with the pKeq, which is always the left acid minus the right. 8 was on the left, 6.9 on the right. KEQ, 10 to the negative 1.1 means you should circle the arrow that goes backwards. Always circle the arrow that goes from the lower pKa to the higher one. Equilibrium always favors the more stable acid over the less stable acid. That's the story of pKa. Saving that. We had another question. Didn't reference any real test questions. When do we have easy isomers? All right. So we have easy isomers when the definitive answer oops, didn't follow my own pattern. When R1 is not equal to R2 and R3 is not equal to R4. In rings, though, only cis is possible. Therefore, no need to say cis. Okay, so this is ring size 7. Size equals 7. Once you get to 8, that's the first time you have a trans versus cis. Got your stop sign, cis, and there is just enough carbons to get from one side to the other. I hope that's 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Trans. So isomerism is possible if alkene is in ring size 8 or higher. Now, it would have been real helpful if that student had come up with the test question where it says, indicate EZ isomerism on this terpene page for all alkenes that exhibit isomerism. I don't have that information available. It happens on about maybe half the tests or a little less. The one from fall 19 was not one of them because, and let's just take a look. I have fall 19 open, that I know. And I'm just going to bring on over the old terpene page. If I can find it there. No. There it is. And we'll just outline why that question was not even included on this page. I know you don't see it yet. I'll just grab the terpenes from the left side of the page. And don't have a new page. Wonderful. Yeah. There's my arrow key. Question number 1. Do these alkenes, and I'll give you the answer, do not exhibit isomerism? And I'm going to put an arrow down here too. And you're saying, wait, Dr. Whitaker, you just said in a ring size 8, they exhibit isomerism. I would like to point out this alkene is also in ring size 5 and 6. It is too small of a ring size. It is too rigid to have any isomer except the one that's drawn. That's what that means. Similarly here, ring size 5 includes this alkene. It is too small to have this bond pointing down and still be able to close the ring. This bond here has to be this direction. It cannot be this direction, or else you cannot close the ring. There's just not enough. I mean, there's too much air, too much space between carbons. So small rings less than 7 or less than 7 do not exhibit isomerism. Does anybody want to interrupt me and give me an actual terpene page that had a double bond that did exhibit isomerism so I can show you what it does to the number of isomers? I'm going to look at my email while I wait, because if that was the last review question, then we're done. We have one here. Last entry.
Yeah, I sent an email, but
yes.
I think I found one for the
cool. For what we're talking about. Yeah, give me a semester.
I think it's spring 2016.
Spring 16 coming up. Give me a second here. Spring 16. I think I had that open. Where's my PDFs? Yes, didn't have to do that. Here it comes. It's far, far down. Yes. Oh yeah, definitely outside that ring. I got to rotate this thing. And I'm just going to grab that molecule. We'll do the stars and the isomerism question part. And then we'll do those other two that you said, Miss Barry. Snipping. Oh, what did I get? I'm clicking too many buttons, guys. Sorry. Close enough. Spring 16. I grabbed the second one. I did that again. I need this one. Got a lot of blank pages today. Need that one. Okay, so one of the questions is to put an asterisk on all the stereocenters. That is never going to go away. Don't put an asterisk here with 2 methyls. Definitely put it there, 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 there. A lot of stereocenters. And of all the double bonds you see here, this is from the other molecule. Of all the double bonds, there's only one that exhibits isomerism. This is in a ring size 6. It can only be done this way. This is in ring size 6, same story. But this can have this bond to the right, or it could have the same bond to the left, in which case it would be Z. And in this one, I want you to write this down on the test. It is a double bond that exhibits isomerism. I will show you the wording of that question. And I'm going to snip it. It's part G. And where are my snip tool? Where'd you go? And the wording is part G. I did it again. This is not fun. This arrow here used to be up here, and they're both arrows, which is messing up my mind. There. So, arrow. That label E is for this right there. If you want to follow all the steps, you cut it in half, you put the missing H's on, and then the 1 is across from the 1, you get E. Now, the answer to the question that's previous to that, determine how many possible stereoisomers there are. I'm not going to copy it. It's on the page. It's always 2 raised to the power of the number of stereocenters. You're supposed to know that already. 2 to the n plus alkenes with isomerism. I know it's a lot of words. What are the options for the alkenes? E and Z. So it's 2 to the power of 3, 6, 7 plus 1, because one of the double bonds can be E or Z. 2 to the 8th. I'm looking for the 8th answer in the multiple choice section. I'm going to just quickly go over there and go back to 8th answer in question 3 or something. Hello. Why are you doing this to me? My Zoom's over my PDF. And now I got to look at it sideways, so you get to look at me having fun here. Yeah. How many possible stereoisomers? 8th answer. 1, 2, 3, 4, 5, 6, 7, 8. 256. There you go. So you got RS possibilities for each stereocenter, and you got EZ possibilities when isomerism is possible. And that's that. And then we have a couple more requests. We'll deal with at least one before we do another break. And it was fall 2019, part 3, 4. That's a multiple choice. Fall 19, not multiple choice, nomenclature, sorry. Fall 19, where'd you go? Is that fall 19? I think so. Fall 19, where are you? There we go. She wanted the, I can't remember. 4-pointer coming up. PDF, snip, 4-pointer part 3. There's my apologies. The 4-pointers at the bottom here. Now I figured out what she was doing. Grab the box and everything. I'm going to do that. You won't have a box. You'll just give me the answer. I did it again. See all the blank pages I'm getting today. that it? There it is. Okay, it's a bicyclo. And what are we going to do with our bicyclo? I did it again. Amazing. Is it here? Yeah. Okay, we got the dots. The dots. Those are the bridgeheads. Which bridge is the largest? I believe it's this one on the bottom. I mean, how many carbons between the dots? And this time is time well spent. 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons between the dots in descending order. The dots are actually in the box too. Going on the top, 1, 2, 3, 4, 5, 6. And the smallest one happens to be in the middle here. It doesn't have to be, but here it is. It's 2. 9 plus 6 plus 2 is 15 plus 2, 17 plus the 2 dots is 19. Non-deca. And why does it end with diene? That's a good question. Non-decadiene. Well, we got to figure out which one's number 1. And it has nothing to do with groups here. You can't violate the rules of bicycle. You got to go to the biggest bridge first. So if you number the biggest bridge starting here, you don't hit the double bond until way later than if you started here. So the most important thing is this first double bond in the biggest bridge, and it's on 2. To get to the other double bond, we're going 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 has a group on it. Might as well put the number there. 12, 13, 14, 15 with a group on 16. Verifying 12, 13, 14, 15, 16, 17. 18 has to be as close to this as possible without being numbered already. 18's here. And 19 as promised, but we already knew that. And the groups on, why the 16's way over there? I don't know. The 16's random. The group on 16 and the group on 2 are identical, and I believe they'll be alphabetically the last group. They start with the letter V. So 2,16 divinyl. And where's the other double bond? Oh, the other double bond is between 15 and 16. That shows up here. That doesn't look so good. There. And this here is a vinyl group. Some of you are saying, wait, that's allele. It's got 3 carbons. And I'm saying, wait, no. Allele has the double bond at the end of a 3-carbon group. This is a vinyl with an extra methyl on carbon 2. So just when I said vinyl was going to be last. No, it is last. The other one's methyl vinyl. It's on 11. Two methyl vinyl. And it's got geometry that's E. It's E. You can say trans, but you know, I like EZ, it's more general. One's on the opposite side of the other one. So yeah, you put it right with the group when it's part of a group. And then all that remains is our stereo center and our double bond with geometry. This would be worth way more than 4 points. I'm getting at least 5. It's a lot of work. It's a good review though. We've got our two types of groups, the vinyl and the methyl vinyl. And we have two stereocenter. Oh, we have a phenyl on one. That's fine. We got room up here. I think I got them all. Stereocenters on 1 and 11. Stereocenter on 1 and 11. And two double bonds with geometry. My goodness. The one on 2 and the one on 15. At least a 6-pointer. I won't do this to you on the test, have a 6-pointer. This reviews everything. Stereo, easy, stereo. Stereo on 1. Stereo on 11. Easy on 2. Easy also on 15. Those are both very big rings, no matter how you cut it. Stereo on 1. Remember, a phenyl looks like this. If we don't know that, then we can't use the priority system that says there's nothing but carbon attached to that carbon. That gives that a clear priority number 1 or 2, based on the fact this also has nothing but carbon. That's a tough call. So our stereocenter is here, and it's going down to a carbon that's got nothing but carbon as well. Which one do I like better? Well, there's an H here, there's an H here, there's an H here, and an H here. But we're coming up to the next carbon, which has just one H, and the next carbon here has 2. So tough call, tough stereocenter. I give you that. It's close, but it goes 1, 2. And definitely the 4 is here. We had a 4. We had a 1. We had a 2. And we definitely have a 3 here. CH2 for 3, CH2 for 4, goes to another CH2, goes to a C with no H's. We have a winner. And of course, the 4 group's not on a wedge or a dash. She picked the hardest nomenclature question she could find. That's what I want to see on review day. All right, 4 switches with 1 to get a double switch going. 4 and 1. That means you better switch 2 and 3 because you want the right answer. And this is a sinister stereocenter, I'll say. Let's do the one on 11. Good practice. 11, we have a 1 for a C with 2 more bonds to C and H. And which of the 3 CH2s hits something last? And I believe it's this one. 1, 2, 3, 4, 5, 6, 7 CH2s. 1, 2, 3, 4. So there's small mercies here. The 4 is on a dash. The 2 is the 19. It hits something way before the 3. 1, 2, 3, connect them. That's clockwise. This one's R. Double bond between 2 and 3. Follow the rules of EZ. I did it again. Okay. 2 mistakes cancel each other. My pen was off. Just doing another copy for E and Z because it's getting a little crowded. Easy. 2 for an H, 1 for a C. Same story as before. There's an H on this C. There's no H's on that C. The ones are on the same side. So 2 is Z. Moving up over here, we'll do it in orange. H, 2, cut here, 1. And then 1 for a C with 1 H and 2 bonds to C. Opposite sides, the ones from each other here, opposite the double bond. It's E on 15. And that's at least a 6-point question, not even a 4. But yeah, if you can do that one, you can do any nomenclature out there. I have to apologize. There was a couple students whose nomenclature by cyclo, or was it the big long alkene? I can't remember. They went past 20 carbons. Had to do a little Googling. Start adding numbers in front of icosane. All right. So I believe we had another question, but I think a break, and then I'm going to go and get the other question from the same student and come back. And if you email me anything right now, we might have time for that too. So we'll see you soon.